1, 2, 3. Let's groove the line. 4, 5, 6. We're feeling fine. Oh yeah. Oh yeah. 7, 8, 9. Keep the rhythm tight. Woo! 10 and beyond, let's funk all night. Count it down, feel the beat. Say what? Numbers groove, make you move on repeat. Step in time, watch them climb, feel the heat. Into the sequence, got you on your feet. 11, 12, 13. Catch the vibe. 14, 14, 15, 16. Come alive. Oh yeah. Oh yeah. 17, 18, 19. Don't stop. 20 and up, we taking it to the top. Count it down, feel the beat. Say what? Numbers groove, make you move on repeat. Step in time, watch them climb, feel the heat. Into the sequence, got you on your feet. Now break it down, break it slow, keep it tight. Feel the groove, let it move, take flight. Oh yeah. From 0 to infinity, we rise. Into your funk, it's no surprise. Oh my. Oh my. Oh my. Count it down, feel the beat. Say what? Numbers groove, make you move on repeat. Step in time, watch them climb, feel the heat. Into the sequence, got you on your feet. Oh yeah. Yeah. Now break it down, break it slow, keep it tight. Feel the groove, let it move, take flight. Oh yeah. From 0 to infinity, we rise. Into your funk, it's no surprise. Oh my, oh my. Now break it down, break it slow, keep it tight. Feel the groove, let it move, take flight. Oh yeah. From 0 to infinity, we rise. Into your funk, it's no surprise. Oh my, oh my. Oh my. Now break it down, break it slow, keep it tight. Feel the groove, let it move, take flight. Oh yeah. From 0 to infinity, we rise. Into your funk, it's no surprise. Oh my, oh my.
Definitions of number, as given by several later mathematicians, make the limit of an infinite sequence identical with the sequence itself. Under this view, the question as to whether the variable reaches its limit is without logical meaning. Thus the infinite sequence 0.9, 0.99, 0.999, is the number 1, and the question, does it ever reach 1, is an attempt to give a metaphysical argument which shall satisfy intuition. Carl B. Boyer, a fellow enthusiast of the J.O.L.A.L.F, embarking on the Introductory sequence course is a fantastic first step. This journey begins by immersing you in the foundational principles that underpin the entire framework. You'll start by exploring the core tenets of joint operations logistics and advanced lifespan forecasting, understanding how these two critical areas intersect and influence one another. The course then delves into the essential terminology and conceptual models that form the bedrock of J.O.L.A.L.F proficiency. You will gain familiarity with the standardized language and analytical structures used throughout the discipline. Building upon this foundational understanding, the curriculum moves into examining the key processes involved in both logistical planning and lifespan prediction. You'll learn about the cyclical nature of these processes and how they contribute to effective operational strategies. Finally, the introductory sequence culminates in an exploration of the fundamental tools and methodologies employed in J.O.L.A.L.F, providing you with a practical understanding of how these concepts are applied in real-world scenarios. This initial phase is designed to provide you with a solid and comprehensive overview, setting the stage for more specialized learning in subsequent modules. A sequence is essentially an ordered list of items. These items can be numbers, letters, objects, or just about anything you can define. What distinguishes a sequence is the specific order in which the elements appear. This order often follows a particular rule or pattern, although not all sequences adhere to such strict predictability. For instance, the numbers 2, 4, 6, 8, and 10 form a sequence where each term is derived by adding 2 to the preceding term. However, a sequence could also be something like the colors of a traffic light in their standard order: red, yellow, green. In this case, the order is based on convention rather than a mathematical formula. Understanding sequences is fundamental in various fields, from mathematics and computer science to music and even linguistics, as they provide a structured way to represent ordered sets of information. The study of sequences often involves identifying the underlying patterns, predicting future terms, or analyzing their properties as they grow or change. Consider the realm of computer science, specifically in the execution of a program. The lines of code are processed in a specific sequence, one after another, unless control flow statements like loops or conditionals dictate otherwise. Point 1, for example, a simple script might first initialize a variable, then perform a calculation using that variable, and finally print the result. The order of these operations is critical. Changing the sequence would likely lead to errors or an incorrect output. This sequential execution is a fundamental aspect of how computers process instructions. In the field of genetics, the sequence of nucleotides in a DNA molecule, adenine, guanine, cytosine, and thymine, determines the genetic code. Point 2, a specific sequence of these bases dictates the production of proteins, which in turn influence an organism's traits. Point 3, a change in the sequence, even a single alteration, can have significant consequences, leading to genetic disorders or variations. The precise order of these biological items is paramount to life itself. Moving to the domain of music, a melody is a sequence of musical notes arranged in a particular order and rhythm. Point 4, the specific sequence of pitches and durations creates a recognizable and often emotionally evocative pattern. Altering the sequence of notes, even slightly, can drastically change the character and impact of the melody. Think of a familiar tune. If the notes were played in a different order, it would no longer be the same melody. In the context of manufacturing and assembly lines, the creation of a product involves a carefully defined sequence of steps. Point 5, for instance, assembling a car requires a specific order of operations: attaching the chassis, then the engine, followed by the body panels, and so on. Deviating from this sequence can lead to inefficiencies, damage to components, or a faulty final product. The ordered progression of tasks is essential for efficient and quality production. Finally, in linguistics, the sequence of words in a sentence determines its meaning. The same words arranged in a different order can convey a completely different idea or even become grammatically incorrect. For example, the cat chased the mouse has a clear meaning, but mouse the chased cat is nonsensical due to the altered sequence of words. The order of linguistic elements is crucial for effective communication. The Journal of Integer Sequences, often abbreviated as JIS, serves as a central hub for researchers and enthusiasts fascinated by ordered lists of whole numbers. Imagine a dedicated space, entirely online and freely accessible to everyone, where the primary focus is the exploration of these numerical patterns. This journal acts as a platform for sharing new discoveries about integer sequences, delving into their inherent characteristics, uncovering their connections to the world of combinations and arrangements, and revealing their surprising appearances in various branches of mathematics and its applications. When someone makes a novel finding about a sequence, or perhaps discovers a new and intriguing sequence itself, they can submit their work to JIS. Experts in the field then carefully review these submissions to ensure that the research is sound and the contributions are original and valuable. Once accepted, these findings are published electronically, making them immediately available to a global audience. This open access format ensures that knowledge about integer sequences can be easily shared and built upon by others. Furthermore, the journal has a strong tie to the online Encyclopedia of Integer Sequences, a vast and ever-growing database of integer sequences. Often, a new sequence that is significant enough to warrant publication in JIS will also be included in the OEIS, further solidifying its place in the mathematical landscape. In essence, the Journal of Integer Sequences is a vital resource for the ongoing study and appreciation of the intricate world of integer sequences. Consider the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8. A case study within JIS might explore a novel connection between this well-known sequence and a seemingly unrelated area, such as the tiling patterns of a specific type of polygon. The study could delve into how the number of ways to tile these polygons with certain shapes is directly related to terms in the Fibonacci sequence, providing a new combinatorial interpretation of these numbers. Another interesting case study could focus on a newly discovered integer sequence arising from a problem in graph theory. Imagine researchers investigating the number of independent sets of a particular family of graphs. They might discover a sequence that counts these sets as the size of the graph increases. A paper in JIS could then analyze the properties of the sequence, derive a recurrence relation that generates its terms, and explore its asymptotic behavior as the graph size grows infinitely large. Furthermore, a study could investigate a sequence that appears in number theory, perhaps related to the distribution of prime numbers or the properties of certain types of divisors. The research might involve using analytical techniques to derive precise formulas or bounds for the terms of the sequence, or it could explore its connections to other important number-theoretic functions. Self-directed study, unveiling the world of integer sequences inspired by the Journal of Integer Sequences. This syllabus outlines a potential path for a self-directed exploration into the fascinating realm of integer sequences, drawing inspiration from the research and content found within the Journal of Integer Sequences JIS. Module 1, Foundations of Sequences and Series. Begin by establishing a solid understanding of the fundamental concepts. Explore the definition of a sequence and its various representations. Differentiate between finite and infinite sequences. Investigate common types of sequences including arithmetic progressions, geometric progressions, and recursively defined sequences. Learn the notations used to describe sequences and series. Understand the concept of a series as the sum of the terms of a sequence. Module 2, Navigating the Online Encyclopedia of Integer Sequences OEIS. Become proficient in utilizing the OEIS as a primary tool for discovery. Learn effective search strategies based on sequence terms, keywords, and properties. Develop the ability to interpret the wealth of information provided for each sequence, including formulas, recurrence relations, generating functions, and links to relevant literature and related sequences. Practice tracing the connections between different sequences and understanding the classification system within the OEIS. Module 3, Techniques for Analyzing Integer Sequences. Acquire a repertoire of methods for investigating the properties of integer sequences. Explore techniques for identifying underlying patterns and formulating conjectures. Learn to derive recurrence relations that define the terms of a sequence based on previous terms. Investigate methods for finding explicit formulas that directly calculate the nth term of a sequence. Study the application of finite differences in identifying polynomial sequences. Introduce the concept and utility of generating functions as a powerful tool for analyzing sequences. Module 4, The Combinatorial Landscape of Integer Sequences. Delve into the profound connections between integer sequences and the art of counting. Explore how numerous integer sequences arise as the solutions to combinatorial problems. Investigate sequences related to permutations, combinations, partitions of integers, and arrangements of objects. Learn the techniques of combinatorial arguments and bijections to establish direct correspondences between abstract sequences and concrete counting scenarios. Analyze case studies of sequences with rich combinatorial interpretations, potentially including examples similar to the Fibonacci sequence and tiling problems. Module 5, Integer Sequences Through the Lens of Number Theory. Explore the intricate relationships between integer sequences and the fundamental properties of numbers. Investigate sequences defined by number-theoretic functions such as the divisor function, Euler's totient function, and the prime counting function. Study sequences related to prime numbers, perfect numbers, and other special classes of integers. Explore concepts of divisibility, modular arithmetic, and their influence on the behavior of integer sequences. Module 6, Advanced Topics and Contemporary Research inspired by J.I.S. Venture into more advanced areas within the study of integer sequences, drawing inspiration from the articles published in the Journal of Integer Sequences. Explore topics such as the asymptotic behavior of sequences and methods for determining their growth rates. Investigate the properties of specific families of sequences, including linear recurrence relations and their characteristic equations, as well as automatic sequences generated by finite automata. Examine applications of integer sequences in diverse fields such as computer science, e.g. analysis of algorithms, physics, e.g. models of physical systems, and biology, e.g. modeling population growth. Engage with current research by reading and attempting to understand articles from the Journal of Integer Sequences, identifying open questions and potential avenues for further exploration. Guiding principles for self-directed learning, active engagement. Don't just read, actively work through examples, try to prove properties, and explore connections. Resource utilization. Make full use of the OEIS, textbooks, online resources, and the Journal of Integer Sequences. Problem solving. Regularly attempt exercises and problems related to each topic to solidify your understanding. Exploration and curiosity. Follow your interests and delve deeper into sequences that pique your curiosity. Reflection and synthesis. Regularly review the material and try to connect different concepts and ideas. It is no great wonder if in long process of time, while fortune takes her course hither and thither, numerous coincidences should spontaneously occur. If the number and variety of subjects to be wrought upon be infinite, it is all the more easy for fortune, with such an abundance of material, to effect this similarity of results. Or if, on the other hand, events are limited to the combinations of some finite number, then of necessity the same must often recur, and in the same sequence. Plutarch's Lives, Volume 2. The excerpt from Plutarch's Lives, as interpreted here, presents a compelling dichotomy regarding the nature of events and the possibility of coincidence. The core idea is that the likelihood of seemingly chance occurrences hinges on the sheer number of possibilities. If the potential ways things can happen are limitless, then over time, coincidences, those surprising and seemingly meaningful concurrences, are bound to arise simply due to the vast number of subjects or elements at play. Think of it like shuffling a deck of cards endlessly. Eventually, you're likely to see the same unusual hand appear again, not because of any grand design, but because there are only so many combinations. Conversely, Plutarch suggests that if the scope of what can happen is actually finite, with a limited number of possible events or states, then the same patterns and combinations must inevitably repeat themselves. This implies a predetermined order, a sequence that will unfold as time progresses. This viewpoint leans towards determinism, the idea that all events are causally determined by prior states. The passage then connects this ancient thought to modern discussions, specifically the tension between free will and determinism. It notes how the idea of a limited number of events leading to predictable sequences resonates with a deterministic worldview. However, the interpretation also brings in the perspective of quantum physics, where the behavior of subatomic particles is often described as probabilistic rather than strictly determined. This introduces the element of chance, suggesting that not everything might follow a fixed sequence. The passage concludes by highlighting this interplay between deterministic and probabilistic viewpoints, emphasizing that the question of whether events follow a predictable path or arise from random processes remains a subject of ongoing debate in both philosophical and scientific inquiry, ultimately touching upon the very limits of our knowledge and understanding of the fundamental nature of reality. Case studies: consider a simple savings account where you deposit the same amount of money each month. The balance of your account over time forms an arithmetic sequence, where each term increases by a constant difference your monthly deposit. Observing the sequence of your monthly balances reveals a predictable pattern of growth. Think about the cooling rate of a hot beverage left on a table. The temperature readings taken at regular intervals will likely form a decreasing sequence. While the exact formula might be more complex, perhaps exponential decay, the ordered list of temperatures shows a clear trend over time. Imagine the number of rabbits in a population that doubles each month. Starting with 2 rabbits, the sequence of the rabbit population each month 2, 4, 8, 16 forms a geometric sequence, where each term is multiplied by a constant ratio, in this case, 2. This demonstrates rapid, predictable growth. Finally, consider the sequence of winning lottery numbers drawn each week. This sequence, ideally, should be random and not follow a discernible pattern. Each week's draw is a term in the sequence, but predicting the next term is generally impossible due to the intended randomness of the selection process. This highlights that not all sequences exhibit a clear, predictable rule. The concept of sequences, as ordered lists of items, has roots stretching back to the very beginnings of human engagement with mathematics and observation of the natural world. Early humans, in their efforts to count, categorize, and understand patterns, inherently dealt with ordered progressions. Think of the simple act of counting on fingers. This generates the fundamental sequence of natural numbers in a specific order. The cyclical nature of seasons, the phases of the moon, and the predictable movements of celestial bodies likely instilled an early awareness of ordered events unfolding over time, which is a form of observing sequences in nature. As civilizations developed, so did more formal mathematical systems. Ancient Babylonian mathematics, for instance, shows evidence of studying arithmetic and geometric progressions in the context of interest calculations and other practical problems. Similarly, Greek mathematicians, such as Pythagoras and his followers, explored sequences of numbers with specific properties, like the square numbers and triangular numbers, often visualizing them geometrically. These early explorations were driven by both practical needs and a philosophical curiosity about the underlying order of the universe. The formalization of sequences as a distinct mathematical object evolved gradually. With the development of algebraic notation and calculus in later centuries, mathematicians gained more powerful tools to define, analyze, and manipulate sequences. Concepts like convergence and divergence of infinite sequences became central to the development of analysis. Over time, the study of sequences branched out into numerous areas of mathematics, including number theory, combinatorics, and the theory of dynamical systems, each contributing its own perspectives and applications. Therefore, the origin of sequences isn't a single event but rather a gradual unfolding alongside humanity's mathematical and scientific understanding, driven by the innate human capacity to recognize and analyze order. Case studies: consider the tally marks used by early humans to keep track of quantities. Each mark added in succession creates a simple sequence representing increasing numbers. 1. This basic form of record-keeping demonstrates an intuitive understanding of ordered progression for practical purposes. Think about the Pythagorean triples, sets of three positive integers a, b, and c, such that a 2 plus b2 equals c2. 2. Ancient mathematicians, like the Babylonians and later the Greeks, discovered and studied these sets, often generating them through specific formulas. 3. The ordered listing of these triples, e.g. 3, 4, 5, 5, 12, 13, etc., represents an early investigation into sequences with specific mathematical properties. Imagine the Fibonacci sequence arising from a problem posed about rabbit populations. 4. While the historical accuracy of Fibonacci's rabbit problem is debated, it serves as a classic example of a sequence defined by a simple recurrence relation that emerges from a seemingly natural scenario. The ordered progression of the number of rabbit pairs 0, 1, 1, 2, 3, 5, illustrates how mathematical sequences can model growth and patterns observed in nature. Consider the development of musical scales. Ancient musical systems involved ordering notes based on specific intervals. The sequence of notes in a scale, like the diatonic scale do, re, mi, fa, sol, la, ti, do, represents an ordered arrangement based on harmonic relationships, demonstrating the early application of sequential ordering in artistic expression. Diophantine sequences are sequences where the terms are integers that satisfy a given Diophantine equation or a system of Diophantine equations. A Diophantine equation, named after the ancient Greek mathematician Diophantus of Alexandria, is a polynomial equation, usually involving two or more unknowns, for which only integer solutions are sought. Therefore, a Diophantine sequence is not defined by a direct formula for its terms based on their position, but rather by the constraint that each term or a set of terms at certain indices must be an integer solution to a specific Diophantine problem. These sequences can arise in various contexts within number theory. For instance, consider the Diophantine equation x2 plus y2 equals z2, which describes Pythagorean triples. A Diophantine sequence could be formed by listing the integer values of x that appear in primitive Pythagorean triples ordered in some way, e.g. by increasing value of z. Similarly, sequences can be generated from solutions to linear Diophantine equations, Pell's equation, or more complex polynomial equations. The defining characteristic is that the terms are integer solutions to a Diophantine problem, and the sequence is formed by ordering a subset of these solutions according to a specific criterion. The study of Diophantine sequences often involves investigating the properties of these integer solutions and the patterns that emerge when they are arranged in a sequence. Imagine the Diophantine equation x plus y equals n, where n is a fixed integer. A Diophantine sequence could be formed by listing the integer values of x that satisfy this equation for positive integer solutions x, y, ordered by the value of x. For example, if n equals 5, the sequence would start 1, 2, 3, 4. Each term is an integer x that is part of an integer solution to the given equation. Consider Pell's equation, a classic Diophantine equation of the form x2 dy2 equals 1, where d is a positive non-square integer. 1 The integer solutions xy to this equation can generate Diophantine sequences. For instance, the sequence of x values from the fundamental and subsequent solutions, when ordered by increasing value, forms a Diophantine sequence where each term satisfies the specific Pell's equation for a given d. Think about the sequence of triangular numbers, 1, 3, 6, 10, 15. These numbers are given by the formula Tn equals 2nn plus 1.2. We can view this as a Diophantine sequence because each term Tn is an integer solution to the equation 2y equals x2 plus x, where y equals Tn and x equals n. The sequence consists of integer values that satisfy this relationship derived from the definition of triangular numbers. An elliptic sequence, at its heart, is a sequence of points on an elliptic curve. To understand this, we first need to picture an elliptic curve itself. It's not an ellipse in the geometric sense, but rather a smooth, projective algebraic curve defined by a specific type of cubic equation, often in the form y2 equals x3 plus x plus b, where a and b are constants. These curves possess a remarkable property: they form an abelian group under a geometrically defined addition operation. Imagine taking 2 points on the curve, you can draw a line through them, and this line will intersect the curve at a third point. Reflecting this third point across the x-axis or a suitable axis depending on the curve's form gives you the sum of the original 2 points. Now, an elliptic sequence arises when you start with an initial point P on the elliptic curve and repeatedly apply this addition operation to itself. The sequence would look like P2 P equals P plus P3 P equals 2 P plus P4 P equals 3 P plus P, and so on. Each term in the sequence is a point on the same elliptic curve, generated by successively adding the initial point P to the previous point in the sequence. The properties of such a sequence depend heavily on the initial point P and the specific elliptic curve on which it resides. For instance, the order of the point P plays a crucial role. If P has finite order n, meaning that np, the sum of P with itself n times, is the identity element of the group, the point at infinity on the projective curve, then the elliptic sequence will be periodic, repeating after n terms. If P has infinite order, the sequence will consist of infinitely many distinct points on the curve. The study of elliptic sequences draws upon concepts from algebraic geometry, number theory, and group theory. These sequences appear in various contexts, including cryptography, where the difficulty of the discrete logarithm problem on elliptic curves is exploited, integer factorization algorithms, and the study of integer points on elliptic curves. The rich algebraic structure of elliptic curves gives rise to fascinating properties of these sequences, making them a subject of deep and ongoing mathematical investigation. Case studies: imagine a cryptographic system based on elliptic curves. You start with a specific point P on a carefully chosen elliptic curve defined over a finite field. Repeatedly adding this point to itself generates a sequence of points P2, P3, P, Kp. The security of the system relies on the difficulty of finding the integer k even if you know the starting point P and the resulting point Kp. This sequence of points generated by repeated addition forms the basis of elliptic curve cryptography. Consider the problem of finding integer solutions to an elliptic curve equation. If you find one integer point P equals xy on the curve, you can repeatedly add it to itself using the elliptic curve group law to generate a sequence of other points 2p, 3p, 4p. While these subsequent points might not always have integer coordinates, the study of the conditions under which the sequence yields further integer points is a significant area of research in number theory. Think about elliptic divisibility sequences EDS. These are integer sequences that arise from division polynomials associated with points on elliptic curves. Point 1 starting with initial integer values related to a point P on an elliptic curve. The subsequent terms of the EDS are generated by a nonlinear recurrence relation that mirrors the point multiplication on the curve. The sequence of integers generated in this way has interesting divisibility properties that are linked to the order of the initial point P on the elliptic curve. The primary sequence of a biological macromolecule, be it a protein or a nucleic acid, fundamentally describes the linear order of its constituent building blocks. For a protein, this signifies the specific arrangement of amino acids linked together by peptide bonds, extending from the amino terminal end to the carboxy terminal end. This precise sequence of amino acids dictates the protein's unique identity and lays the groundwork for its subsequent folding and ultimate function. Similarly, for a nucleic acid like DNA or RNA, the primary sequence refers to the ordered arrangement of nucleotides along the sugar phosphate backbone. In DNA, these nucleotides contain one of four bases: adenine, guanine, cytosine, and thymine, while RNA utilizes uracil instead of thymine. This specific sequence of bases carries the genetic information, providing the instructions for building and operating a living organism. Therefore, the primary sequence, in both proteins and nucleic acids, represents the one-dimensional, covalent structure and serves as the foundational blueprint for the macromolecule's higher-order structures and biological roles. Case studies: consider the hemoglobin protein in red blood cells. Its primary sequence, the specific order of its roughly 574 amino acids, is crucial for its function of carrying oxygen. 1 A single amino acid substitution in this primary sequence, as seen in sickle cell anemia where valine replaces glutamic acid at a specific position, dramatically alters the protein's shape and its ability to bind and transport oxygen, leading to a serious genetic disorder. 2 This highlights how a change in the primary sequence can have profound biological consequences. Think about the insulin hormone. The primary sequence of insulin, a relatively small protein, consists of two polypeptide chains linked together. 3 The exact order of its amino acids is essential for its ability to bind to insulin receptors and regulate blood sugar levels. Even slight alterations in this primary sequence can result in the production of inactive or less effective insulin, as seen in some forms of diabetes. 4 Imagine the genetic code encoded in DNA. A specific primary sequence of nucleotides in a gene dictates the order of amino acids in the protein that gene encodes. 5 For example, the sequence ATG serves as a start codon, signaling the beginning of a protein coding region, while sequences like TAA, TAG, and TGA act as stop codons, signaling the end. 6 A mutation that changes even a single nucleotide in this primary sequence can lead to a different amino acid being incorporated into the protein, potentially altering its function. Consider the ribosomal RNA rRNA, a key component of ribosomes, the protein synthesis machinery of the cell. 7 The primary sequence of rRNA contains specific regions that are complementary to messenger RNA mRNA and transfer RNA tRNA, allowing for the correct translation of the genetic code into proteins. Variations in the primary sequence of rRNA can affect the efficiency and accuracy of protein synthesis. 8 These short examples illustrate how the precise linear order of building blocks in biological macromolecules, their primary sequence, directly dictates their structure and function, and how even small changes in this fundamental sequence can have significant biological effects. The terms sequence and series, while related, describe distinct mathematical concepts. A sequence, as we've discussed, is an ordered list of items, often numbers, that follow a specific rule or pattern. For instance, 2, 4, 6, 8. is a sequence of even numbers. A series, on the other hand, is the sum of the terms of a sequence. So, taking the previous sequence, the corresponding series would be 2 plus 4 plus 6 plus 8 plus. The act of summing the elements of a sequence transforms it into a series. Series can be finite, meaning they have a limited number of terms, or infinite, containing an endless number of terms. For a finite sequence, its corresponding series will also have a finite sum. However, the behavior of infinite series is more complex and intriguing. An infinite series may converge to a finite value, meaning that as you add more and more terms, the sum gets closer and closer to a specific number. For example, the series 1 plus 21 plus 41 plus 81 plus converges to 2. Conversely, an infinite series may diverge, meaning its sum grows without bound or oscillates without approaching a specific value, as seen with the series 1 plus 2 plus 3 plus 4 plus. Understanding the conditions under which an infinite series converges or diverges is a fundamental topic in calculus and analysis. Various tests, such as the ratio test, the integral test, and the comparison test, are employed to determine the convergence behavior of infinite series. Case studies: consider a simple interest calculation. If you deposit a principal amount and earn a fixed amount of interest each year, the total amount in your account at the end of each year forms an arithmetic sequence. 1. The series formed by summing the interest earned each year up to a certain point gives you the total interest accumulated. Imagine a ball dropped from a height where it rebounds to half the height of the previous bounce. The sequence of the heights of each successive bounce, e.g. 1 meter, 0.5 meter, 0.25 meter, is a geometric sequence. The series formed by summing the total vertical distance traveled by the ball downward and upward over an infinite number of bounces converges to a finite value, even though the sequence of bounce heights never reaches zero. Think about a geometric series used in finance, like a perpetuity. A perpetuity is a stream of equal payments that continues indefinitely. 2. The sequence of these payments is constant. The series representing the present value of all future payments converges to a finite amount based on the discount rate, illustrating the concept of an infinite series with a finite sum in a practical application. Consider the harmonic series, 1 plus 21 plus 31 plus 41 plus. The sequence of terms n1 approaches 0 as n increases. 3. However, the corresponding series diverges, meaning its sum grows infinitely large. This case study highlights that even if the individual terms of a sequence get very small, their sum can still be infinite. Sequence analysis is a broad and powerful field that involves examining the order of elements within a sequence to extract meaningful information. This could apply to a vast array of sequences, from the order of nucleotides in DNA or RNA, to the sequence of amino acids in proteins, to the sequence of words in a text, or even the sequence of events in a time series. The fundamental goal is to understand the patterns, relationships, and structures inherent in the arrangement of these elements. In biology, sequence analysis of DNA, RNA, and proteins is crucial for understanding gene function, protein structure and activity, evolutionary relationships, and disease mechanisms. Techniques like sequence alignment are used to compare sequences and identify similarities or differences, which can reveal conserved regions, mutations, or evolutionary links. Phylogenetic analysis uses sequence data to reconstruct evolutionary trees, showing the relationships between different organisms or genes. Motif searching aims to identify short, recurring patterns within sequences that may have functional significance. Beyond biology, sequence analysis finds applications in various other domains. In linguistics, it's used to study the structure of language, identify patterns in text, and perform tasks like authorship attribution. In computer science, It's fundamental to algorithms for data compression, pattern recognition, and artificial intelligence, such as analyzing sequences of user actions or network traffic. In finance, time series analysis involves examining sequences of stock prices or economic indicators to identify trends and make predictions. The specific tools and techniques used in sequence analysis vary depending on the type of sequence and the questions being asked, but the underlying principle remains the same: extracting knowledge from the order of elements. Case studies: imagine analyzing customer purchase histories at an online retailer. The sequence of items a customer buys over time can reveal patterns in their preferences, predict future purchases, or identify shopping trends. Point 1, for example, someone who frequently buys coffee beans, a specific type of filter, and a particular brand of coffee maker might be targeted with offers related to coffee subscriptions or accessories. Sequence analysis here helps tailor marketing strategies. Think about monitoring network traffic for security purposes. The sequence of packets sent and received by a computer can be analyzed to detect anomalies that might indicate a cyber attack. Point 2, a sudden and unusual sequence of connection attempts to multiple servers could trigger an alert, highlighting a potential security breach. Sequence analysis in this context is crucial for real-time threat detection. Consider the analysis of musical compositions. The sequence of notes, chords, and rhythms in a piece of music defines its melody, harmony, and structure. Analyzing these sequences can help identify musical styles, determine authorship, or even generate new music with similar characteristics. Computational musicology heavily relies on sequence analysis techniques. Imagine studying user interactions with a software application. The sequence of buttons clicked, menus accessed, and data entered can provide insights into how users navigate the software, identify usability issues, or personalize the user experience. Point 3, analyzing these interaction sequences can inform interface design and feature development. An archaeological sequence refers to the chronological ordering of events, layers, strata, features, and artifacts within an archaeological site or across a region. It's about understanding what happened first, second, third, and so on, building a timeline of past human activity. This sequencing is fundamental to interpreting the history and development of a site and the cultures that inhabited it. Archaeologists establish these sequences through various methods. Stratigraphy is a cornerstone, relying on the principle of superposition, which states that in undisturbed layers, the oldest are typically found at the bottom and the youngest at the top. By carefully excavating and recording these layers and the artifacts found within them, a relative sequence of deposition can be established. Artifacts found in the same layer are generally contemporaneous. Typology and seriation are also crucial. Typology involves classifying artifacts based on their style, form, and material, recognizing that these characteristics often change gradually over time. Seriation then arranges these artifact types into a chronological sequence based on their popularity. The idea is that a particular style will emerge, become popular, and then gradually decline in favor of new styles. By analyzing the frequencies of different artifact types in different layers or assemblages, archaeologists can create a relative sequence. Cross-dating link sequences from different sites. If a specific artifact type or style with a known date range is found at multiple locations, it can help synchronize the sequences of those sites. Finally, absolute dating methods, such as radiocarbon dating or dendrochronology tree ring dating, provide calendar dates for specific materials found within the sequence, anchoring the relative sequences in absolute time. The integration of these various approaches allows archaeologists to construct detailed and nuanced chronological frameworks for understanding the past. Case studies: consider the excavation of J.O.L.A.L.F, a mound formed by successive human settlements over long periods. 1 As archaeologists dig down, they uncover layers representing different occupation phases. 2 Artifacts found in deeper layers, like pottery of a specific style, are understood to be older than those found in the layers above. 3 The sequence of pottery styles across the strata helps build a chronological sequence of the site's inhabitants and their cultural changes over centuries. Imagine the analysis of a cemetery. Different burial types, grave goods, and even the orientation of the bodies might change over time. By carefully recording these variations across different burials and applying relative dating techniques based on artifact styles found within the graves, archaeologists can establish a sequence of burial practices, reflecting evolving social structures or beliefs within the community that used the cemetery. Think about studying a series of superimposed floors in an ancient house. Each floor level represents a period of occupation. Artifacts sealed beneath a later floor are older than those found on or above it. The sequence of floor construction and the associated artifacts, pottery fragments, tools, etc., provide a microchronology of the house's use and any changes in domestic life over its lifespan. Consider the analysis of obsidian hydration layers on stone tools found at different archaeological sites in a region. The thickness of the hydration layer, a chemical weathering process, can be used to estimate the age of the tool. 4 By comparing the hydration layer thicknesses of similar tool types across various sites, archaeologists can develop a relative sequence of obsidian use and potentially link the occupation periods of these different locations. 5 Becoming truly skilled at using the online Encyclopedia of Integer Sequences, or OEIS, is like learning to navigate a vast and intricate library dedicated entirely to ordered lists of whole numbers. It involves more than just typing in a few numbers and hoping for a match. You need to develop strategic approaches to searching. This might mean knowing how to input the first few terms of a sequence you've encountered, or understanding how to use relevant keywords that describe the sequence's origin or properties. You'll also learn to search based on specific mathematical characteristics that a sequence might possess. Once you find a sequence in the OEIS, you'll encounter a wealth of information, and becoming proficient means knowing how to decipher it all. This includes understanding the formulas that generate the terms of the sequence, the recurrence relations that define a term based on previous ones, and the powerful tool of generating functions that can encapsulate the entire sequence in a single algebraic expression. Furthermore, you'll learn to follow the links provided to related sequences, exploring how different mathematical ideas connect and intertwine. Finally, you'll gain an understanding of the OEIS's own internal organization, its classification system, which helps you to categorize and contextualize the sequences you discover within the broader landscape of integer sequences. This comprehensive skill set transforms the OEIS from a simple database into a powerful instrument for mathematical exploration and discovery. Case studies: imagine you've stumbled upon the sequence 1, 3, 6, 10, 15 while working on a combinatorial problem involving the number of ways to choose pairs from an increasing number of items. Initially, you might just input these few terms into the OEIS search bar. If you're proficient, you'll also consider variations, like starting from 0 if that feels more natural to your problem, or perhaps entering just a subset of the terms in case of initial errors in your derivation. The OEIS quickly identifies this as the sequence of triangular numbers A000217. Now, a novice user might just note the name. But a proficient user will delve deeper. They'll examine the formula provided, nn plus 1 2. They'll check if this formula aligns with their combinatorial understanding. They'll look at the recurrence relation, an equals an1 plus n, and see how each term builds upon the previous one by adding the index, which might offer a different perspective on their original problem. They'll also note the generating function, a more advanced concept, but one that a proficient user recognizes as a powerful tool for further analysis. Furthermore, the proficient user will explore the links section. They might find connections to sequences counting the number of edges in a complete graph or the number of ways to choose two items from n+1. These links could provide alternative combinatorial interpretations of the triangular numbers, potentially offering new insights into the original problem they were tackling. They might also notice the formula section, which could present alternative ways to express the same sequence, perhaps revealing connections to other mathematical areas. Finally, the proficient user will observe the classification of the sequence, perhaps seeing it listed under figure-8 numbers. This categorization helps them understand where the sequence fits within the broader mathematical landscape, potentially leading them to explore other related sequences like square numbers or pentagonal numbers, which might be relevant to future problems. Consider another scenario where you're investigating a sequence with a more complex pattern, say, 1, 1, 2, 5, 14, 42. A less experienced user might struggle to find a match with just these few terms. However, a proficient user will try different search strategies. They might try searching with keywords related to how the sequence was generated, if they have any intuition. They might also look for properties, like whether the terms are always even or odd, or if the differences between consecutive terms follow a recognizable pattern, and then search based on these properties if the initial term search is unsuccessful. Once a match is found in this case, Catalan numbers, A000108, the proficient user will again leverage the wealth of information. They'll examine the multiple formulas provided, realizing that each one often corresponds to a different combinatorial interpretation of the Catalan numbers, such as counting balanced parentheses or the number of binary trees. Understanding these diverse interpretations significantly enhances the user's mathematical toolkit. Consider the Bell numbers A000110. This sequence counts the number of partitions of a set of n labeled elements. For example, if you have a set of 3 elements 1, 2, 3, they can be partitioned in 5 ways: 1, 2, 3, 1, 2, 3, 1, 3, 2, 2, 3, 1, and 1, 2, 3. The Bell numbers appear in various combinatorial problems, including counting rhyme schemes of poems. Think about the Catalan numbers A000108. We briefly mentioned them, but their occurrences are so widespread they deserve more attention. They count a remarkable variety of seemingly unrelated combinatorial objects, such as the number of ways to correctly match pairs of parentheses, the number of binary trees with n nodes, the number of paths on a grid that do not go above the diagonal, and the number of ways to triangulate a convex polygon. Their ubiquitous nature makes them a cornerstone of combinatorics. Imagine the Moeskin numbers A001006. This sequence counts the number of ways of drawing non-intersecting chords on a circle with n points. They also appear in various other contexts, such as counting paths on a 1D grid that stay between -1 and 1, and the number of rooted trees with n leaves where each internal node has at least 2 children. Consider the Fibonacci numbers with even indices A001519, 0, 1, 3, 8, 21, 55. This is a subsequence of the Fibonacci sequence where we only take the terms at even positions starting index from 0. This sequence has its own interesting properties and recurrence relations. Think about the number of primes less than or equal to NA000720, denoted by pi n. This fundamental sequence in number theory charts the distribution of prime numbers as n increases. Understanding the behavior of the sequence is a central goal of prime number theory. You'll begin by exploring various approaches to spot patterns within a sequence, developing your intuition for recognizing arithmetic progressions, geometric progressions, or more complex relationships. This involves looking for consistent differences between terms, constant ratios, or other recurring structures that might suggest an underlying rule. Once you've identified a potential pattern, you'll learn how to formalize this into a conjecture, an educated guess about the sequence's general behavior. A key skill you'll develop is the ability to express a sequence through a recurrence relation, which defines each term based on one or more preceding terms, allowing you to generate subsequent values step by step. You'll also delve into methods for finding explicit formulas, which provide a direct way to calculate any term in the sequence based solely on its position, without needing to know the previous terms. For sequences where the pattern seems to be related to powers of n, you'll study the technique of finite differences, which can help you identify if a sequence is generated by a polynomial and determine the degree of that polynomial. Finally, the module introduces the powerful concept of generating functions, which are essentially power series whose coefficients are the terms of the sequence. You'll learn how these functions can be manipulated algebraically to derive properties of the sequence, find recurrence relations, and even obtain explicit formulas, providing a sophisticated and often elegant approach to sequence analysis. Case studies: consider the Fibonacci sequence A000045, 0, 1, 1, 2, 3, 5, 8, 13. The OEIS entry for the sequence is a treasure trove of analysis. You'll find the fundamental recurrence relation, Fn equals Fn1 plus Fn2 with initial conditions F0 equals 0 and F1 equals 1.1. The entry also provides the explicit formula Benet's formula, Fn equals 5Nn, where equals 21 plus 5 is the golden ratio. Furthermore, the generating function for the Fibonacci sequence is given as 1x x2 x.2. Analyzing this generating function can lead to the recurrence relation and the explicit formula. While finite differences aren't the most direct way to analyze Fibonacci numbers due to their exponential growth, the OEIS entry touches upon related sequences where differences might play a role. Another compelling case is the Catalan numbers A000108, 1, 1, 2, 5, 14, 42, 3. The OEIS entry reveals a rich set of properties and ways to analyze them. One prominent feature is their recurrence relation, Cn equals sigma I equals 0 n1 ci Cn1 I for n greater than or equal to 1, with C0 equals 1.4. The entry also gives the explicit formula, Cn equals n plus 11 n2 n.5. The generating function for the Catalan numbers is Cx equals 2x114x, and this function satisfies the algebraic equation xc(x2 cx plus 1 equals 0, which is closely linked to the recurrence point 6. Again, while finite differences aren't the primary tool here, the OEIS entry explores connections to other sequences where this technique might be more applicable. Consider a simpler example where finite differences shine, the sequence of square numbers A000290, 0, 1, 4, 9, 16, 25, 7. Taking the first differences yields 1, 3, 5, 7, 9. And the second differences give 2, 2, 2, 2. The constant second difference indicates that the original sequence is a polynomial of degree 2, which we know to be n2. The OEIS entry confirms this and might point to other polynomial sequences where finite differences are a key analysis technique. Finally, let's look at how generating functions can be powerful. Consider the sequence of all ones, 1, 1, 1, 1. A 0 0 0 0 1 2. Its generating function is simply 1x1. By manipulating this function, e.g. differentiating, integrating, we can derive generating functions for related sequences, like the sequence of natural numbers 1, 2, 3. With generating function 1x 2x. The OEIS entries for these basic sequences often highlight the elegance and utility of generating functions in analyzing their properties and relationships. A linear recurrence in sequences is a rule that defines each term of a sequence as a linear combination of one or more preceding terms. This means that to find the next number in the sequence, you take the previous terms, multiply each by a constant, and then add these products together. The linear aspect refers to the fact that the previous terms appear with an exponent of 1, there are no squares, cubes, or other nonlinear functions of the preceding terms involved. Case studies: consider the population growth of a species where the number of individuals in the next generation depends on the number in the two preceding generations, perhaps reflecting the time it takes to mature and reproduce. This can be modeled by a linear recurrence of order 2, like Pn equals APn1 plus Bpn2, with initial populations P0 and P1 given point 1. In computer science, the number of steps an algorithm takes to solve a problem of size n might be defined by a linear recurrence. For example, the time complexity Tn could follow Tn equals 2 Tn1 plus 1 with T0 equals 1, indicating that solving a problem of size n involves solving two subproblems of size n1 and doing a constant amount of additional work. Think about the number of ways to tile a 2 times n rectangle with dominoes. Let an be the number of ways. You can find that an equals an1 plus an2, with a 1 equals 1 and a 2 equals 2. This is the Fibonacci recurrence, arising from a combinatorial problem. Module 4, the combinatorial landscape of integer sequences, invites you to explore the deep and often surprising ways in which ordered lists of whole numbers emerge from the fundamental act of counting. It's about recognizing that many sequences aren't just abstract mathematical entities but rather the numerical footprints of solutions to various counting problems. This module will guide you through investigating how sequences naturally arise when you consider different ways of arranging objects, permutations, selecting subsets combinations, breaking down numbers into sums partitions, and generally organizing discrete items. You'll learn the art of constructing combinatorial arguments, which involve reasoning about how to count specific arrangements or selections, and how these counting processes directly lead to the terms of an integer sequence. A particularly powerful technique you'll explore is the concept of bijections, which involves establishing a one-to-one correspondence between the elements you're counting and the terms of a sequence, providing a clear and direct link between the abstract numbers and the concrete objects. Throughout this module, you'll analyze various case studies, potentially revisiting the Fibonacci sequence through its connection to tiling problems or exploring other sequences that have elegant and insightful combinatorial interpretations, revealing the hidden counting stories behind the numbers. Case studies: consider the sequence 1, 2, 6, 24, 120. This arises from counting the number of ways to order n distinct objects, which is n. N factorial. The sequence directly reflects the combinatorial problem of permutations. Think about the sequence 1, 3, 6, 10, 15. These are the triangular numbers, which count the number of ways to choose two items from a set of n plus 1 items, given by the combination formula 2n plus 1. The sequence embodies the combinatorial concept of combinations. Imagine the sequence 1, 1, 2, 3, 5, 7, 11. This sequence counts the number of ways to partition an integer n into distinct parts. For example, 5 can be partitioned into distinct parts in three ways: 5, 4 plus 1, 3 plus 2. This sequence emerges from the combinatorial problem of integer partitions with a specific constraint. Consider the sequence 1, 1, 1, 2, 3, 4, 6. This sequence counts the number of partitions of an integer n into any number of parts. For example, 3 can be partitioned as 3, 2 plus 1, 1 plus 1 plus 1. This illustrates a different type of integer partition problem leading to a distinct sequence. Sequential factoring, in the context of number theory, refers to the process of finding the prime factors of a composite number by systematically testing potential divisors in increasing order. You start by attempting to divide the number by the smallest prime, 2. If it divides evenly, you record 2 as a factor and continue the process with the resulting quotient. You repeat this with 2 until it no longer divides the quotient evenly. Then, you move to the next smallest prime number, 3, and repeat the division process. You continue this with subsequent prime numbers 5, 7, 11, and so on until the remaining quotient is either 1, meaning you've found all prime factors, or a prime number itself, which is then the final factor. The efficiency of sequential factoring depends on the size of the smallest prime factor of the number. If a number has a small prime factor, sequential factoring will find it relatively quickly. However, if the prime factors are large, this method can become very time-consuming, especially for large numbers. For instance, factoring a number that is the product of two large prime numbers of roughly the same size would require testing all primes up to the square root of that number, which can be computationally infeasible for numbers used in modern cryptography. While simple to understand and implement, sequential factoring is generally not the most efficient algorithm for factoring large numbers, and more sophisticated methods are employed in practice. Case studies: imagine you want to find the prime factors of the number 12. Using sequential factoring, you first try dividing by 2. 12 divided by 2 is 6, with no remainder. 0.1, so 2 is a factor. Now you try dividing the quotient, 6, by 2 again. 6 divided by 2 is 3, with no remainder. So, 2 is a factor again. Now you try dividing the new quotient, 3, by 2. It doesn't divide evenly. So, you move to the next prime number, 3. 3 divided by 3 is 1, with no remainder. So, 3 is a factor. Since the quotient is now 1, you've found all the prime factors of 12, 2, 2, and 3. Consider factoring the number 35. You start by trying to divide by 2. It doesn't divide evenly. Next, you try 3. It also doesn't divide evenly. Then you try the next prime, 5. 35 divided by 5 is 7, with no remainder. So, 5 is a factor. Now you try dividing the quotient, 7, by 5. It doesn't divide evenly. The next prime is 7. 7 divided by 7 is 1, with no remainder. So, 7 is a factor. The quotient is now 1, so the prime factors of 35 are 5 and 7. Now, think about factoring a larger number, say 91. You try dividing by 2, no, 3 no, 5 no. You then try 7. 91 divided by 7 is 13, with no remainder. So, 7 is a factor. Now you try dividing 13 by primes less than or equal to its square root, which is roughly 3.6. You've already tried 2 and 3, and 13 isn't divisible by them. Since 13 itself is prime, it's the next factor. So, the prime factors of 91 are 7 and 13. Module 5, Integer Sequences Through the Lens of Number Theory, shifts our focus to the profound relationships between integer sequences and the intrinsic properties of numbers themselves. Here, you'll discover how sequences can be defined by fundamental concepts from number theory, such as the divisor function, which counts the number of divisors of an integer, Euler's totient function, which counts the positive integers up to a given integer that are relatively prime to it, and the prime counting function, which tells you how many prime numbers there are up to a certain value. You'll also delve into sequences that are directly related to special classes of integers, like prime numbers themselves, perfect numbers which are equal to the sum of their proper divisors, and other fascinating numerical entities. This module will also explore how core number theoretic ideas like divisibility rules and modular arithmetic can influence the patterns and behavior of integer sequences, revealing deeper connections between the ordered lists and the fundamental building blocks of mathematics. Consider the sequence that gives the number of divisors of each positive integer: 1, 2, 2, 3, 2, 4, 2, 4, 3, 4. This sequence is directly defined by the divisor function, a fundamental concept in number theory. Each term a(n) is sigma 0 n, the count of positive divisors of n. Think about the sequence of Euler's totient function values: 1, 1, 2, 2, 4, 2, 6, 4, 6, 4. Here, the nth term n counts the positive integers less than or equal to n that are relatively prime to n.1. The sequence arises directly from a key number theoretic function related to multiplicative properties of integers. Imagine the sequence of prime numbers: 2, 3, 5, 7, 11, 13. This sequence is defined by a fundamental property of integers, primality. The nth term, if we consider it starting from the first prime, is the nth prime number. Its study is central to number theory. Consider the sequence of perfect numbers: 6, 28, 496, 8128. These are numbers equal to the sum of their proper divisors. This sequence is defined by a specific number theoretic property and has been studied since antiquity. Nested sequences without bullet points use indentation and numbering or lettering to show the hierarchy of items. Each level of the sequence is indented further than the level above it. The items within each level are typically numbered or lettered sequentially. This creates a clear visual structure indicating which items belong to which higher level categories. For example, a main point might be numbered with an Arabic numeral 1, 2, 3, subpoints under it might be lettered with capital letters A, B, C, and further subpoints could use lowercase Roman numerals I, 2, 3. This method allows for organizing information with multiple layers of detail without relying on bullet point symbols. Case Study 1, Software Documentation. A software manual needs to explain the steps for a complex feature. Instead of using bullet points, it employs a numbered nested sequence. Initiate the process. Select the Start button from the main interface. Navigate to the Modules menu. I choose the specific module required for this feature. To confirm the module selection, configure the settings. Access the configuration panel. Adjust the necessary parameters. A. Input the required numerical values. B. Select the appropriate options from the drop-down menus. Execute the function. Click the Run command. Monitor the progress in the status bar. This structure clearly shows the main stages and the sub-steps involved within each stage, making it easy for the user to follow the instructions. Case Study 2, Recipe Instructions. A detailed baking recipe uses a combination of numbered and lettered nested sequences to organize the preparation steps. Prepare the ingredients. A. Measure all dry ingredients accurately. B. Ensure wet ingredients are at the correct temperature. Mix the dry ingredients. Combine flour, sugar, and baking powder in a bowl. Whisk thoroughly to ensure even distribution. Combine wet and dry ingredients. A. Gradually add the wet ingredients to the dry mixture. B. Mix until just combined, avoiding overmixing. Bake the batter. Preheat the oven to the specified temperature. Pour the batter into the prepared pan. Bake for the indicated time. The nesting helps differentiate between preparing ingredient groups and the subsequent steps of mixing and baking. Case Study 3, Project Outline. A project manager creates an outline for a new initiative using a nested sequence. Phase 1, Planning. Define project scope and objectives. Identify key stakeholders. A. Internal team members. B. External clients. Develop a detailed timeline. Phase 2, Execution. Task assignment to team members. Regular progress meetings. Quality assurance checks. Phase 3, Closure. Final deliverable submission. Stakeholder feedback collection. Project review and documentation. This hierarchical structure allows for a clear understanding of the project's stages and the specific activities within each phase. To understand these advanced sequences, mathematicians use a variety of powerful techniques. They analyze the remainders when the terms are divided by a fixed number to find repeating patterns and divisibility rules. They also use a method of representing sequences as special kinds of mathematical functions called generating functions, which allows them to find formulas for the terms and understand their long-term behavior. Concepts from PADIC analysis help in studying sequences in the PADIC number system. The theory of Diophantine equations is used to investigate sequences whose terms satisfy specific equations involving whole numbers. Tools from calculus and complex analysis are employed to study the distribution and properties of number sequences, particularly those related to prime numbers. Ideas from algebraic number theory, which deals with extensions of the rational numbers, are used to understand sequences that arise in these more abstract settings. Finally, computational number theory develops algorithms to generate and analyze these number-theoretic sequences. Examples of advanced topics include understanding how prime numbers are distributed within specific sequences, studying the properties of Lucas sequences and their use in testing for prime numbers, investigating sequences formed by points on elliptic curves, analyzing how sequences behave when considered modulo powers of prime numbers, studying Fibonacci-like sequences in the PADIC number system, examining sequences generated by simple rules applied repeatedly, and exploring the connections between number sequences and dynamical systems. Overall, advanced sequence number theory is a fascinating and complex area that combines the study of patterns in numbers with the fundamental principles of number theory, with connections to many other areas of mathematics and computer science. Case Study 1, Primolity Testing via Lucas Sequences. Lucas sequences, defined by linear recurrences, possess number-theoretic properties related to the primolity of integers. 1 By examining the terms of specific Lucas sequences modulo a number n, one can derive conditions that, if met, strongly suggest or in some cases prove that n is prime. This is a more advanced method than simple trial division and forms the basis of efficient primolity tests used in cryptography. Case Study 2, Distribution of primes in arithmetic progressions. Dirichlet's theorem on arithmetic progressions, a cornerstone of analytic number theory, concerns the sequence AA plus DA plus 2D. It proves that if A and D are co-prime integers, this sequence contains infinitely many prime numbers. The proof involves advanced techniques from complex analysis and the study of Dirichlet-L functions, demonstrating deep connections between sequences and the distribution of primes. 2. Case Study 3, Elliptic Curve Cryptography. Elliptic curves, defined by cubic equations, have a group structure. 3 Sequences of points on these curves, generated by repeated addition, have number theoretic properties that are crucial for modern cryptography. The difficulty of the discrete logarithm problem on these sequences forms the basis for secure communication protocols. Case Study 4, PADIC Fibonacci Sequence. Considering the Fibonacci sequence in the field of PADIC numbers reveals different convergence properties compared to the real numbers. For example, the PADIC Fibonacci sequence exhibits periodicity modulo powers of p. Studying such sequences provides insights into the behavior of familiar number sequences in alternative number systems. Module 6, Advanced Topics and Contemporary Research inspired by JIS, serves as a bridge to the cutting edge of research in the field of integer sequences, drawing its inspiration directly from the articles published in the Journal of Integer Sequences. This module will introduce you to more sophisticated concepts, such as the asymptotic behavior of sequences, which involves studying how the terms of a sequence grow or change as the index becomes very large, and the mathematical tools used to determine these growth rates. You'll investigate specific families of sequences that exhibit interesting and complex structures, including linear recurrence relations and the powerful technique of using their characteristic equations to find closed-form solutions, as well as automatic sequences, which are generated by finite automata, revealing a surprising link between number theory and computation. Furthermore, this module will explore the diverse applications of integer sequences in various scientific and technical fields, such as their role in the analysis of algorithms in computer science, their use in modeling physical systems, and their application in understanding population growth in biology. Finally, and perhaps most excitingly, you'll be encouraged to engage with current research by reading and attempting to understand articles from the Journal of Integer Sequences, fostering a sense of active participation in the ongoing exploration of these fascinating mathematical objects and potentially identifying open questions and avenues for your own future exploration. Consider the Fibonacci sequence's growth. Its OEIS entry A000045 details its asymptotic behavior, showing that Fn5n for large n, where is the golden ratio. This analysis of its growth rate is a key advanced topic. Think about the Thue-Morse sequence A000069, an automatic sequence generated by a simple rule involving counting ones in binary representations. 1 Its study involves finite automata and reveals complex properties, illustrating the connection between sequences and computation. Imagine the analysis of the time complexity of a recursive algorithm where the number of operations Tn follows a linear recurrence like Tn equals 2Tn1 plus n. Solving this recurrence using its characteristic equation provides the asymptotic growth rate of the algorithm, a crucial application in computer science. Consider research in the Journal of Integer Sequences that analyzes a newly discovered sequence related to the energy levels of a quantum system. Such studies often involve determining the asymptotic behavior of the sequence to understand the system's properties at high energy levels. Recursive sequences are number sequences where each term is calculated based on the values of the terms that came before it. To get started with a recursive sequence, you need to know the value s of the initial term s. Then, a specific rule or formula tells you how to find any subsequent term using the preceding ones. For instance, the well-known Fibonacci sequence follows the rule that each number is the sum of the two numbers before it, starting with 0 and 1. Another example is a sequence where each number is found by doubling the previous number and adding 1, given a starting value. Recursive sequences can produce a wide variety of patterns, from simple to very intricate, depending on the rule and the starting values. Finding a direct formula to calculate any term in the sequence based only on its position in the sequence can be difficult. These sequences are important in many areas of study, including mathematics, computer science for things like designing algorithms and data structures, and even in describing patterns observed in the natural world. When studying recursive sequences, mathematicians often look at how they behave in the long run, whether they settle down to a specific value, grow indefinitely, or repeat in a cycle. The number of previous terms needed to calculate the current term determines the order of the recursive sequence. For example, the Fibonacci sequence is a second-order sequence because you need the two previous terms. Case Study 1, Population Growth. A biologist models a rabbit population where each pair of adult rabbits produces a new pair of offspring each month, and offspring become adults after 1 month. If we start with one pair of newborn rabbits, the population growth follows a recursive pattern similar to the Fibonacci sequence. Point 1 Let Rn be the number of rabbit pairs in month n. R0 equals 0 newborn, R1 equals 1 adult pair. Then Rn equals Rn1 plus Rn2 for n greater than or equal to 2, where Rn1 represents the existing adult pairs and Rn2 represents the pairs that were newborns 2 months ago and are now adults producing offspring. This recursive model helps predict population size over time. Case Study 2, Compound Interest. Consider an initial investment of P0 in an account that earns a fixed interest rate R compounded annually. The amount of money Pn in the account at the end of year n can be modeled recursively as Pn equals 1 plus Rpn1. Starting with P0, each year's balance is determined by multiplying the previous year's balance by the growth factor 1 plus R. This recursive relationship is fundamental to understanding how investments grow over time. Case Study 3, Tower of Hanoi Puzzle. The classic Tower of Hanoi puzzle involves moving a stack of n disks from one peg to another, following specific rules. Point 2 Let Mn be the minimum number of moves required to solve the puzzle with n disks. The optimal strategy involves recursively moving the top n1 disks to the auxiliary peg, then moving the largest disk to the target peg, and finally moving the n1 disks from the auxiliary peg to the target peg. This leads to the recursive relation Mn equals 2 Mn1 plus 1, with M1 equals 1. Analyzing this recursion provides the minimum number of steps needed for any number of disks. Case Study 4, Computer Algorithm, Factorial. The factorial of a non-negative integer n, denoted by n, can be defined recursively. Point 3 The base case is 0, equals 1. For n0, n, equals n times n1. This recursive definition mirrors how a computer program might calculate the factorial by calling itself with a smaller input until it reaches the base case. The exploration of sequences extends into the realm of algebraic structures, where sequences are not merely lists but elements within formal mathematical systems. Consider a sequence defined over a finite field, where terms are elements of a set with a fixed number of elements, and operations like addition and multiplication follow specific rules modulo a prime number. Such sequences often arise in coding theory, where the order of symbols in a code word determines its error-correcting capabilities. For instance, a linear feedback shift register sequence, generated by a recurrence relation over a finite field, produces a periodic sequence used in cryptography and communication systems. The study of these sequences involves analyzing their period length and distribution properties, which are critical for ensuring secure data transmission. Generating the sequence A initialize the register with a starting configuration of bits. B. Apply the feedback polynomial to compute each subsequent term. I. Multiply the current terms by coefficients of the polynomial. 2. Sum the results modulo the field characteristic. C. Continue until the sequence repeats, revealing its period. Analyzing properties A. Determine the period length using the characteristic polynomial. B. Study the distribution of terms to ensure randomness-like behavior. I. Count occurrences of each field element. To compare to expected uniform distribution for cryptographic strength. This structured approach highlights the interplay between sequence generation and its practical applications, emphasizing the ordered progression of steps in both creation and analysis. Sequences also play a pivotal role in dynamical systems, where the evolution of a system over time can be represented as a sequence of states. Consider a discrete dynamical system defined by a function f, where the next state is obtained by applying f to the current state, starting from an initial value x_0. The sequence x_0, fx_0, ffx_0 describes the system's trajectory. In chaotic systems, small changes in x_0 lead to vastly different sequences, a phenomenon studied through sequence analysis to understand long-term behavior. For example, the logistic map x_n+1 equals rx_n1, x_n generates a sequence that, for certain values of r, exhibits chaotic behavior, with terms oscillating unpredictably yet remaining bounded. Analyzing such sequences involves computing statistical measures like the Lyapunov exponent to quantify sensitivity to initial conditions. Defining the system A, select the function f and parameter r. B, choose an initial state x_0 within the appropriate domain. I, ensure x_0 lies within the interval 0, 1 for the logistic map. 2. Verify r is within the range producing chaotic behavior. Generating and analyzing the sequence A, iterate the function to produce terms x_1, x_2, x_3. B. Compute statistical properties to classify the sequence's behavior. I. Calculate the Lyapunov exponent to measure divergence. 2. Plot the sequence to visualize periodic or chaotic patterns. This nested structure organizes the process of studying dynamical sequences, reflecting the hierarchical nature of defining, generating, and analyzing system behavior. The study of sequences also intersects with probabilistic methods, particularly in random sequences and their applications. In probability theory, a sequence of random variables represents outcomes of repeated experiments, such as coin flips or stock price movements. The sequence of heads and tails in a series of coin flips, for instance, can be analyzed to study properties like the expected number of runs, consecutive identical outcomes. Such sequences are modeled using stochastic processes, where each term is drawn from a probability distribution, and the order reflects temporal progression. Advanced techniques, such as martingale theory, are used to analyze the expected behavior of these sequences, with applications in financial modeling and algorithm design. Modeling the random sequence A, define the probability space and random variables. B. Specify the distribution for each term. I. For a coin flip, use a Bernoulli distribution with p equals 0.5. 2. For stock prices, model with a geometric Brownian motion. Analyzing sequence properties A. Compute expected values for key statistics, like run lengths. B. Apply probabilistic tools to study long-term behavior. I. Use martingale properties to assess fairness in gambling models. 2. Analyze convergence to equilibrium distributions. This structured approach to random sequences underscores the importance of order in probabilistic settings, connecting sequence analysis to real-world phenomena. Sequence synthesis involves the creation or generation of a sequence of elements, often numbers, symbols, or other data, based on a specific rule, algorithm, or set of constraints. This process can be deterministic, where the same input always produces the same output sequence, or stochastic, where randomness plays a role in the generation. One common method is defining a sequence using an explicit formula, where each term can be directly calculated based on its position in the sequence. For example, the sequence of even numbers can be synthesized using the formula n equals 2n, where n is the index starting from 1. Another approach is through recursion, where each term is defined in relation to one or more preceding terms, requiring initial values to start the sequence. The Fibonacci sequence, where each term is the sum of the two preceding ones, is a classic example of synthesis by recursion. Sequence synthesis is fundamental in various fields, including mathematics for exploring number patterns, computer science for generating data structures and algorithms, signal processing for creating waveforms, and bioinformatics for modeling biological sequences like DNA. The complexity of the synthesis process can range from simple arithmetic progressions to the generation of highly intricate and seemingly random sequences using sophisticated algorithms. Constraints can also be imposed on the synthesized sequence, such as requiring specific statistical properties, adherence to a particular pattern, or optimization based on a defined objective function. In essence, sequence synthesis is the art and science of creating ordered collections of elements according to a defined procedure or set of rules. Case Study 1, Generating Musical Melodies. A music composition software uses algorithms to synthesize musical note sequences. One simple method involves defining a starting note and a set of rules for the interval pitch difference to the next note. For example, a rule might dictate a sequence of intervals like up a major third, down a minor second, up a perfect fifth. Starting with AC4, the software synthesizes the melody, E4, D4, A4, and so on. More complex algorithms can incorporate musical scales, chords, and probabilistic elements to generate richer and more varied musical sequences. Case Study 2, Creating Pseudo-Random Number Generators (PRNGs). Computer systems rely on PRNGs to generate sequences of numbers that appear random but are actually produced by deterministic algorithms. 1. A common type is a linear congruential generator (LCG), defined by the recursive formula xn plus 1 equals axn plus c mod m, where a, c, and m are constants, and x0 is the seed value. 2. By choosing appropriate parameters, an LCG can synthesize a sequence of integers within the range 0m1 that exhibits statistical properties approximating true randomness, crucial for simulations, cryptography, and gaming. 3. Case Study 3, Synthesizing DNA Sequences for Biotechnology. In synthetic biology, researchers often need to create custom DNA sequences. 4. Software tools can synthesize these sequences based on desired protein outputs or specific functional elements. 5. The synthesis process involves determining the order of nucleotide bases adenine, guanine, cytosine, thymine according to the genetic code or other design principles. Constraints like codon optimization, choosing synonymous codons to enhance protein expression, are often incorporated into the synthesis algorithm. Case Study 4, Generating Textures for Computer Graphics. Computer graphics artists use algorithms to synthesize textures for 3D models. 6. One approach involves using cellular automata, where a grid of cells evolves over time based on a set of rules applied to neighboring cells. 7. Starting from a small seed pattern, the iterative application of these rules can synthesize complex and visually interesting patterns that can be used as surface textures. Different rule sets lead to a wide variety of synthesized textures, from organic-looking patterns to abstract designs. Sequence total refers to the sum of all the terms within a given sequence. If the sequence is finite, the sequence total is simply the arithmetic sum of its elements. For example, the sequence 2, 4, 6, 8 has a sequence total of 2 plus 4 plus 6 plus 8 equals 20. For infinite sequences, the concept of a sequence total becomes more complex and is related to the idea of an infinite series. The total of an infinite sequence is defined as the limit of the partial sums of its terms. If this limit exists and is finite, the infinite series is said to converge to that total. For instance, the infinite geometric series 1 plus 1 2 plus 1 4 plus 1 8 plus has a sequence total or sum of 2, as the partial sums approach 2 as more terms are added. However, if the limit of the partial sums does not exist or is infinite, the infinite series is said to diverge, and thus does not have a finite sequence total. Understanding the convergence and divergence of infinite series is a crucial aspect of determining their sequence totals. Various tests, such as the ratio test, the integral test, and the comparison test, are used to analyze the convergence of infinite series and find their sums when possible. The sequence total provides a single numerical value that summarizes the cumulative value of all the elements in the sequence, whether it is finite or, in the case of convergence, infinite. Case Study 1, Calculating Total Sales Over a Quarter. A retail business tracks its weekly sales. The weekly sales figures for a 13-week quarter form a finite sequence, 1,200, 1,500, 1,100. 1,350. To determine the total revenue for the quarter, the business calculates the sequence total by summing all 13 weekly sales figures. This single value provides a summary of the overall sales performance during that period. Case Study 2, Total Distance Traveled in Discrete Steps. A robot moves in discrete steps. The length of each step in centimeters forms a sequence, 10, 12, 9, 15, 8. To find the total distance the robot has traveled after these 5 steps, we calculate the sequence total by adding the length of each step, 10 plus 12 plus 9 plus 15 plus 8 equals 54 centimeters. Case Study 3, Total Value of an Infinite Geometric Series in Physics. In physics, consider a ball dropped from a height that rebounds to a fraction r of its previous height after each bounce 0 r1. The total vertical distance traveled by the ball is the sum of the initial drop and the distances of all subsequent upward and downward movements. This forms an infinite geometric series where the sequence total represents the total distance. If the initial drop is h, the total distance is h plus 2r, h plus 2r2, h plus 2r3, h plus dot equals h plus 2hr plus r2 plus r3 plus equals h plus 2h1r, r equals h1r1 plus r. This shows how the sequence total of an infinite sequence can have a physical interpretation. Case Study 4, Total Amount of Medication Administered Over Time. A patient receives a daily dose of a certain medication. The sequence of daily dosages, which might be constant or change over time, represents a sequence. Point 1. To find the total amount of medication administered over a specific period, the total of the sequence is calculated by summing the daily doses for the duration of the treatment. I believe in logic, the sequence of cause and effect, and in science its only begotten Son, our law, which was conceived by the ancient Greeks, thrived under Isaac Newton, suffered under Albert Einstein. That fragment of a creed for materialism which a friend in college had once shown him rose through Donald's confused mind. John Brunner. Appendix A, Infinite Series. A.1 What are infinite series? An infinite series is the process of adding up all the terms in an infinite sequence, which is an ordered list of items that goes on forever. Instead of stopping after a few terms, an infinite series tries to capture the total sum of this endless list. The key question is whether the sum settles on a definite value or grows endlessly, perhaps even behaving unpredictably. To understand this, we look at partial sums, which are the totals obtained by adding only the first few terms of the sequence, stopping at different points. If these partial sums gradually approach a specific value as more terms are added, the series is said to converge, meaning it has a finite sum. If the partial sums keep growing, fluctuate wildly, or never settle, the series diverges, indicating no single sum exists. This concept is vital for studying sequences, as it connects to their long-term behavior and applications across various fields. 8.2 Types of infinite series. Infinite series come in different forms, depending on the patterns in their sequences or how their partial sums behave. Series from steady-step sequences. These series come from sequences where each term increases by a fixed amount compared to the previous one, like a list of odd numbers. Adding these terms often leads to partial sums that grow without stopping, so the series diverges, as the totals become increasingly large. Series from shrinking step sequences. In these series, each term is a fixed fraction of the previous term, creating a sequence that gets smaller with each step. If the terms shrink quickly enough, the partial sums may approach a definite value, meaning the series converges. If the terms don't shrink enough, the series may still diverge, with sums growing endlessly. Series from reciprocal sequences. Consider a sequence where terms are reciprocals of increasing quantities, like the reciprocals of consecutive numbers. Even though the terms get smaller, adding them up can result in partial sums that grow slowly but endlessly, causing the series to diverge. Series with specific patterns. Some series follow a pattern where the terms are reciprocals of quantities raised to a certain power. If the terms shrink rapidly due to a high power, the series may converge. If the terms don't shrink enough, the series diverges. 8.3 Ways to test series behavior. To determine whether a series converges or diverges, mathematicians use several methods to analyze the sequence S terms or partial sums, checking term behavior. If the terms of the sequence don't get close to zero as you go further along, the series cannot converge, so it diverges. However, even if the terms do shrink toward zero, the series might still diverge, so more tests are needed. Comparing term ratios. This method looks at the ratio between consecutive terms in the sequence. If this ratio consistently becomes smaller than a certain threshold, the series is likely to converge. If the ratio grows larger, the series diverges. If the ratio hovers around a neutral point, the test doesn't give a clear answer. Relating to continuous functions, if the sequence S terms can be thought of as values of a smooth, decreasing function, you can study the behavior of that function over an infinite range. If the total area under this function is finite, the series converges. If it's infinite, the series diverges. Comparing to known series. By comparing the sequence S terms to those of a series whose behavior is already known, you can infer whether the new series converges or diverges. If the terms are smaller than those of a converging series, the new series likely converges too. If they're larger than those of a diverging series, it diverges. Handling alternating terms. For series where terms alternate between positive and negative, convergence can occur if the terms gradually get smaller and approach zero. This test ensures the partial sums stabilize rather than oscillate indefinitely. 8.4 Connection to sequences. Infinite series are deeply linked to sequences because the partial sums form a sequence of their own. The convergence of a series depends on whether the sequence of partial sums settles on a specific value. Series also help analyze sequences in other ways. Encoding sequences, a special kind of series, called a generating function, can represent an entire sequence by assigning its terms as coefficients in a power series. This tool helps uncover patterns or relationships within the sequence. Understanding growth. The behavior of a series can reveal how quickly or slowly the terms of its sequence diminish, providing insights into the sequence's long-term properties. 8.5 Applications of infinite series. Infinite series are not just abstract ideas, they appear in many practical and theoretical contexts, connecting to the course's interdisciplinary focus, mathematics. Series help solve problems in number theory and analysis, such as finding precise values for mathematical constants. Physics, the total distance traveled by an object that bounces with decreasing heights can be modeled as a series, showing how physical processes can have finite outcomes despite infinite steps. Computer science, series are used to analyze how many steps an algorithm takes, especially for processes that break problems into smaller parts. Finance, the value of a stream of payments that continues forever can be calculated as a series, helping determine fair prices for financial agreements. 8.6 Case Studies. A philosophical paradox: imagine someone moving halfway to a goal, then halfway again, and so on, forever. The distances form a sequence, and adding them as a series shows the total distance is finite, resolving the paradox by showing the process completes in a definite way. Function representations. Below is a proposed Appendix B, convergence tests for the described course on integer sequences. This appendix focuses on the tests used to determine whether infinite sequences and series converge or diverge, tailored to complement the course's emphasis on sequences and their properties. It avoids equations and numbers, as per your request, using plain language to describe concepts, methods, and examples. The appendix aligns with the self-directed learning approach of the course, incorporates interdisciplinary connections, and references the philosophical context from Carl B. Boyer's quote about limits and sequences. Appendix B, Convergence Tests. B.1 Introduction to Convergence Tests. In the study of sequences, which are ordered lists of items that continue indefinitely, a key question is what happens to the terms as you look further along the list. Do they settle close to a single value, or do they grow, shrink, or fluctuate without settling? This behavior is called convergence if the terms approach a specific value, or divergence if they don't. For infinite series, which involve adding up all the terms of a sequence, we ask whether the running totals of these terms stabilize at a definite sum or grow endlessly. Convergence tests are methods to determine whether a sequence or series converges or diverges. These tests are essential tools for analyzing the long-term behavior of sequences and series, connecting to the course's exploration of mathematical patterns and their applications in fields like computer science, biology, and physics. B.2 Why convergence tests matter. Convergence tests help us understand whether a sequence or series has a predictable outcome. For a sequence, this means checking if its terms consistently approach a single value. For a series, it involves examining whether the partial sums totals of the first few terms settle on a specific value as more terms are added. These tests are crucial because they allow us to make sense of infinite processes, like those in the course's case studies of population growth, algorithm efficiency, or physical systems. The philosophical insight from Carl B. Boyer, who noted that an infinite sequence is identical to its limit in modern mathematics, underscores the importance of these tests. They provide a rigorous way to define that limit, avoiding vague questions about whether a sequence reaches its destination. B.3 Common convergence tests for sequences. While sequences are often analyzed directly by observing their terms, convergence tests help confirm whether they approach a limit. Here are key methods used. Observing term behavior. One way to test a sequence is to examine whether its terms get closer to a specific value over time. If the terms don't approach zero or a single value but instead grow large or oscillate, the sequence likely diverges. For example, a sequence where each term is the reciprocal of a larger and larger quantity typically converges to zero, as the terms shrink steadily. Comparing to known sequences. By comparing a sequence's terms to those of a sequence whose behavior is already understood, you can infer convergence. If the terms are similar to or smaller than those of a sequence known to converge, the new sequence may also converge. If they resemble a diverging sequence, divergence is likely. Checking consistency. For some sequences, especially those defined by a rule relating each term to previous ones, you can test whether the terms stabilize by examining how they change. If the difference between consecutive terms shrinks consistently, the sequence may converge to a fixed point. B.4 Convergence tests for series. Series, which sum the terms of a sequence, require specific tests to determine if their partial sums converge. Below are widely used methods. Term size test. If the terms of a sequence don't shrink toward zero as you move along the list, the series cannot converge, as the partial sums will keep changing significantly. This test is a quick way to spot divergence, but if the terms do approach zero, further tests are needed, as the series might still diverge. Ratio comparison. This method involves looking at the ratio between consecutive terms in the series. If this ratio consistently becomes smaller than a certain threshold, suggesting the terms shrink rapidly, the series is likely to converge. If the ratio grows or stays large, the series diverges. If the ratio hovers around a neutral point, the test is inconclusive. Function-based test. If the sequence S terms can be thought of as values of a smooth, decreasing function, you can study that function S behavior over an infinite range. If the total area under this function is finite, the series converges. If it's infinite, the series diverges. This test connects the discrete world of series to continuous mathematics. Series comparison. By comparing the terms of a series to those of a known series, you can determine its behavior. If the terms are smaller than those of a series known to converge, the new series likely converges too. If they're larger than those of a diverging series, it diverges. This method relies on having a library of familiar series for comparison. Alternating term test. For series where terms switch between positive and negative, convergence can occur if the terms steadily get smaller and approach zero. This ensures the partial sums oscillate less and less, eventually settling close to a single value. B.5 Connection to the course. Convergence tests are woven throughout the course S modules, particularly in analyzing sequences and series. Module 1 Foundations. Tests like observing term behavior help learners understand basic sequence convergence, such as sequences of reciprocals or ratios of combinatorial numbers. Module 3 Analytical Techniques. Methods like ratio comparison and function-based tests are used to study properties of integer sequences, such as those counting arrangements or divisors. Module 6 Advanced Topics. Convergence tests apply to studying the long-term growth of sequences, like those arising in algorithm analysis or physical models, where determining whether some stabilize is critical. The course S case studies, such as modeling population growth or cryptographic sequences, rely on these tests to predict outcomes or ensure reliability. Boyer's quote, which emphasizes that an infinite sequence is its limit, aligns with these tests by providing precise tools to define that limit, avoiding philosophical ambiguities about infinite processes. B.6 Applications of convergence tests. Convergence tests have practical and theoretical significance, connecting to the course S interdisciplinary focus, mathematics. They help determine whether sums of terms, like those related to counting patterns or number properties, yield definite values, as seen in number theory problems. Computer science. Tests are used to analyze whether recursive algorithms produce stable results or to assess the efficiency of processes that sum infinite steps. Physics. In models of systems like bouncing objects or energy levels, convergence tests confirm whether total quantities, like distance or energy, remain finite. Biology. When modeling population dynamics or genetic sequences, these tests help predict whether growth rates stabilize or explode. B.7 Case studies. Decimal approximation. Boyer's insight. Consider a sequence where each term adds another 9 to a decimal, like a number starting with a single 9 after the decimal point, then 2 nines, then 3, and so on. Testing convergence shows the terms approach a whole number, confirming they are identical to that number, as Boyer suggests, with no need to ask if they reach it. Growth ratios, a sequence of ratios between consecutive terms in a pattern, like those counting ways to arrange objects, may converge to a specific value, such as a ratio tied to natural growth patterns. Convergence tests confirm this behavior, relevant to combinatorial studies in the course. Random processes, in analyzing sequences from random experiments, like averaging outcomes of repeated trials, convergence tests help determine if the averages settle on an expected outcome, connecting to probabilistic models in the course. B.8 Learning Tips. To master convergence tests, try these strategies from the course's guiding principles: active exploration, work through examples by hand, like testing a sequence of shrinking terms or a series with alternating signs, to build intuition. Use resources, consult the online encyclopedia of integer sequences to find sequences with known convergence properties, comparing their behavior to your own examples. Problem solving, practice applying each test to different sequences or series from the course's case studies, such as those in music or genetics, to see how they reveal patterns. Reflect and connect. Think about how convergence tests relate to Boyer's idea that a sequence is its limit, considering how these tests make that concept precise. This appendix provides a conceptual overview of convergence tests, avoiding mathematical equations and numbers while maintaining clarity and relevance to the course. It connects to Boyer's quote by emphasizing the precision of limits in modern mathematics and supports the course's interdisciplinary and self-directed learning goals. Appendix C, Philosophical and Historical Context of Sequences. C.1 Why explore the philosophy and history of sequences? Sequences, as ordered lists of items that often follow a pattern, are more than mathematical tools. They reflect humanity's quest to understand order, infinity, and the nature of reality. This appendix delves into the philosophical and historical roots of sequences, connecting to the course's focus on their properties and applications. By examining how thinkers have grappled with sequences over time, learners can better appreciate their significance, especially in light of Carl B. Boyer's insight that an infinite sequence is identical to its limit, and Plutarch's reflection on recurring patterns in finite or infinite systems. This exploration enriches the course by situating sequences within broader intellectual debates, making abstract concepts more meaningful. C.2 Philosophical Perspectives on Sequences. The idea of a sequence and ordered progression of items raises deep questions about infinity, determinism, and the nature of limits. Boyer's view, which equates an infinite sequence with its limit, emphasizes a modern mathematical stance where the process of approaching a value is inseparable from the value itself. This perspective resolves ancient puzzles, like the question of whether a sequence reaches its limit, by defining the sequence as its endpoint in a precise, logical way. For example, a sequence that gets closer and closer to a specific value is not striving toward it but is, in essence, that value when viewed infinitely. This clarity avoids metaphysical debates, aligning with the course's rigorous approach to sequences and series. Plutarch's quote, on the other hand, explores sequences in a broader sense, suggesting that in an infinite realm of possibilities, patterns and coincidences are inevitable, while in a finite system, the same sequences must repeat. This raises philosophical questions about whether the universe follows predictable sequences determinism or allows for chance probabilistic outcomes. In the course, sequences like those modeling population growth or cryptographic systems reflect this tension between order and randomness, inviting learners to consider whether patterns in nature or mathematics are destined to repeat or emerge by chance. C.3 Historical evolution of sequences. The study of sequences has evolved alongside human thought. Early humans observed sequences in nature. Think of the repeating phases of the moon or the progression of seasons, which likely sparked an intuitive sense of order. Ancient civilizations formalized these ideas. Babylonian mathematicians explored sequences in practical contexts, like calculating growth over time, while Greek thinkers, such as Pythagoras, studied sequences of numbers with special properties, like those forming geometric shapes. These early investigations blended practical needs with a philosophical curiosity about the universe's structure. As mathematical tools advanced, sequences became central to understanding infinity and change. In later centuries, the development of precise notation and methods allowed mathematicians to analyze sequences more systematically, particularly in studying how terms behave over an infinite span. This led to modern concepts of convergence, where sequences are defined by their long-term behavior, as Boyer describes. The course's focus on tools like the online Encyclopedia of Integer Sequences (OEIS) and the Journal of Integer Sequences continues this tradition, providing a platform for exploring sequences in a rigorous, collaborative way. C.4 Connection to the course. This appendix ties directly to the course's modules and guiding principles. Module 1 Foundations. Understanding the historical context of sequences helps learners appreciate why definitions of sequences and series matter, grounding abstract concepts in human discovery. Module 6 Advanced Topics. Philosophical questions about infinity and determinism connect to advanced topics like asymptotic behavior and automatic sequences, which explore long-term patterns and computational rules. Exploration and curiosity. Reflecting on philosophical and historical ideas encourages learners to ask big questions, aligning with the course's emphasis on following one's interests. Boyer's quote is explicitly addressed in Module 1 by discussing how modern mathematics resolves ancient debates about limits, while Plutarch's perspective informs Module 6's exploration of sequences in probabilistic and dynamical systems. These connections make the course more thought-provoking, encouraging learners to see sequences as both mathematical and philosophical objects. C.5 Applications in Philosophy and History. Philosophical and historical perspectives on sequences have practical implications. Mathematics, historical debates about infinity shaped modern definitions of convergence, which are central to analyzing sequences in the course. Philosophy, questions about determinism versus chance, as raised by Plutarch, inform discussions of sequences in random processes, like those in biology or cryptography. Interdisciplinary studies, understanding the cultural history of sequences, e.g. in ancient music or astronomy, connects mathematical patterns to human creativity and observation. C.6 Case studies. Ancient paradoxes. Imagine a philosophical puzzle where someone moves halfway to a goal, then halfway again, endlessly. Ancient thinkers debated whether the goal is ever reached. Modern sequence analysis, as Boyer suggests, shows the total distance forms a series that converges to a definite value, resolving the puzzle logically. Celestial patterns. Early astronomers observed sequences in the positions of stars or planets. These observations led to mathematical models of orbits, which the course connects to sequences in dynamical systems. Determinism in nature. A sequence modeling a biological population might repeat or stabilize, echoing Plutarch's idea of recurring patterns. Analyzing such sequences philosophically questions whether nature follows fixed or random paths. C.7 Learning tips. To engage with this appendix, use the course's principles. Active engagement. Reflect on how Boyer's and Plutarch's ideas relate to sequences you study. such as those in the OEIS. Resource utilization: read historical accounts of mathematical discoveries in the Journal of Integer Sequences or related texts to see how sequences shaped thought. Reflection and synthesis: journal about how philosophical questions about infinity or order connect to the course's mathematical tools, deepening your understanding. Appendix D: Practical applications and interdisciplinary case studies. D.1 Why focus on applications and case studies? Sequences are not just abstract lists, they solve real problems and connect to diverse fields, from technology to art. This appendix highlights practical applications of sequences and provides case studies that show their impact across disciplines. By grounding the course's mathematical concepts in real-world scenarios, it makes the material more accessible and engaging, especially for learners new to sequences or those from non-mathematical backgrounds. These examples also reinforce the course's interdisciplinary focus, showing how sequences bridge mathematics with computer science, biology, music, and more, enhancing the relevance and excitement of the self-directed study. D.2 Practical applications of sequences. Sequences appear in countless practical contexts, reflecting their versatility. Computer science: the order of operations in a program forms a sequence, where each step must follow the previous one correctly to produce the desired output. Analyzing these sequences ensures efficient and error-free code. Biology: the arrangement of building blocks in DNA or proteins forms a sequence that determines an organism's traits. Studying these sequences helps decode genetic information or design treatments. Music: a melody is a sequence of notes, where the order creates a recognizable tune. Changing the sequence alters the music's emotional impact. Manufacturing: assembly lines follow a sequence of steps to build products. The correct order ensures efficiency and quality. Linguistics: the sequence of words in a sentence conveys meaning. Rearranging the order can change or destroy the message. These applications show how sequences are embedded in everyday systems, making the course's concepts relatable to real-world challenges. D.3 Interdisciplinary case studies. The following case studies illustrate how sequences are applied across fields, connecting to the course's modules and themes. Cryptographic sequences in cybersecurity: in computer security, sequences generated by specific rules protect data. For example, a system might use a sequence of values to create encryption keys, where the order ensures only authorized users can decode messages. This relates to Module 6's exploration of automatic sequences and their computational properties. Learners can explore how these sequences must be unpredictable yet repeatable, tying to the course's focus on pattern analysis. Genetic sequences in medicine: the sequence of components in a DNA strand determines how a gene functions. Scientists analyze these sequences to identify mutations linked to diseases, like a single change causing a health issue. This connects to Module 5's number theoretic sequences, as genetic patterns can be studied mathematically. The case study makes sequences tangible for biology enthusiasts, showing their life-saving potential. Musical sequences in composition: a composer creates a melody by arranging notes in a sequence, where the order evokes specific emotions. Changing the sequence can transform the melody's mood. This links to Module 4's combinatorial sequences, as note arrangements can be counted and analyzed. This case study appeals to creative learners, showing how mathematics enhances art. Archaeological sequences in history: archaeologists use sequences of artifact layers to build timelines of past cultures. Each layer's position in the sequence indicates its age, helping reconstruct historical events. This relates to Module 1's foundational sequence definitions and Module 3's analytical techniques. The case study connects sequences to storytelling, engaging history buffs. Financial sequences in investment, the growth of savings in an account, with regular deposits, forms a sequence where each term depends on the previous balance. Analyzing the sequence predicts future wealth. This ties to Module 3's recurrence relations and Module 6's asymptotic behavior, showing practical financial modeling. This case study makes sequences relevant to everyday decision-making. D.4 Connection to the course. These applications and case studies integrate with the course's structure. Module 1 Foundations. Case studies like archaeological sequences reinforce the importance of order in defining sequences. Module 3 Analytical Techniques. Financial and genetic sequences show how recurrence relations and pattern analysis solve real problems. Module 4 Combinatorial Landscape. Musical sequences highlight combinatorial counting in creative contexts. Module 5 Number Theory. Genetic sequences connect to number theoretic properties, like modular patterns in DNA analysis. Module 6 Advanced Topics. Cryptographic sequences align with automatic sequences and computational applications. The case studies also reflect Boyer's idea that sequences are their limits by showing how practical outcomes, e.g. secure encryption, healthy genes, depend on precise sequence behavior. Plutarch's perspective on recurring patterns is evident in applications like archaeology, where sequences reveal historical cycles. Reference and citation: A Handbook of Integer Sequences by J.O.L.A.L.F. The Encyclopedia of Integer Sequences by J.O.L.A.L.F. and S. Plouffe. Sequences by Heini Halberstam and Klaus Roth. The Online Encyclopedia of Integer Sequences by J.O.L.A.L.F.
One, two, three, let's groove in line. 4, 5, 6, we're feeling fine. Oh yeah. 7, 8, 9, keep the rhythm tight. 10 and beyond, let's funk all night. Count it up, count it down, feel the beat. Say what? Numbers prove, make you move on repeat. Step in time, watch 'em climb, feel the heat. Oh snap, oh snap. Integer sequence got you on your feet. Ooh-wee. Ooh-wee. 11, 12, 13, catch the vibe. 14, 15, 16, come alive. Oh yeah. 17, 18, 19, don't stop. Ooh. 20 and up, we taking it to the top. Ooh-wee. Count it up, count it down, feel the beat. Say what? Numbers prove, make you move on repeat. Step in time, watch 'em climb, feel the heat. Oh snap, oh snap. Integer sequence got you on your feet. Ooh-wee. Now break it down, break it slow, keep it tight. Feel the groove, let it move, take flight. Oh yeah. From 0 to infinity we rise. Woo. Integer